Okay, so let's look at 33E. So it's an ellipse oriented counterclockwise. And we want to find a parameterization for it. So it's the sum of the distance between 1 and -1 is 4. If we were to write it in this is tricky. I don't remember off the top of my head how to do this, but let's go for it. Okay, so here's -1 and here's 1. And those are going to be the foci of the ellipse. Now, the distance between z and 1 plus the distance between z and -1 is going to add up to 4. So that means that if you go over here to 2, that point, the distance between -1 and 2 is 3. And that distance is 1. So those two distances add up to 4. So that point is on the ellipse, as well as this point here, -2. Okay, so those points are on the ellipse. Okay, now, question is, what point up here on the y-axis is going to be on the ellipse? And so let's see here. If we call that, we'll call that y sub 0, the point that's on the ellipse up here. If this distance from here to here is going to be the distance between 0, comma y0 and that point and the point 1, 0. Okay, so that's the square root of 1 squared plus y0 squared. Okay, now that distance is going to be the same as this distance here. And those two have to add up to 4. So that means this one has to add up to 2. So that means that this has to be, in order for this to happen, 1 plus y0 squared has to be 4, which means that y0 squared has to be 3. So this is going to be the square root of 3. Okay, and so then the ellipse is going to look something like this. Something like that, although that's probably not a very good drawing. And the equation of the ellipse is going to be x squared over 2 squared, or put it this way, x squared over 4. Wait, let's do this. Over 2 squared plus y squared over, now this is going to look weird, it's the square root of 3, because y0 is the square root of 3. Square root of 3 squared equals 1. Okay, so that's the equation if we were in rectangular coordinates. Okay, are you guys familiar with this? With how ellipses, how equations of ellipses are?
Yes.
Okay, that's good. Okay, so now what we do here is similar to what we did with the circle. Basically, if you look at it this way, you have x over 2 squared plus y over root 3 squared equals 1. And so what you want to do is, there's a trigonometric identity that you guys all know, where it's something squared plus something else squared equals 1, right? You remember what that is? It's a common trigonometric.
Sine squared.
Yes, cosine squared plus sine squared. So what you want to do is you want to make this the cosine. We'll use a t. And you want to make this one be sine t. Okay. I think we're running out of space. Let me continue this. Okay, so we'll continue this up here. Dang, no, that doesn't work. Okay, so we'll continue this. I'll draw the arrow this way. We'll continue this right here. Okay. So we have x of t equals 2 cosine t, and we have y of t equals, I'm just solving for x and y, equals the square root of 3 sine t. And so the parameterization of the ellipse oriented counterclockwise is going to be 2 cosine t, because that's our x part, plus the y part, or this is the real part, and then the imaginary part is going to be root 3 I sine t, like that. And then you can let t go from 0 to 2 pi, and that will do it. Okay, so if you put cosine first, sine second, or the cosine on the real part, sine on the imaginary part, and then whatever angle you have, whatever value of t is going to actually correspond to the angle. So this is going to be, this point right here will be z of 0. Okay, when t is 0, you'll get this point. And when t is pi over 2, you'll get this point. And you can verify that, because if you plug in a 0, that zeroes out, right? You just have, this is 1, so that's going to be 2. If you put pi over 2 in, this is 0, this is 1, so you're going to get root 3i. You're going to get this point right here. And so as you go along, it's going to go around this way, going around the curve this way, which is the counterclockwise direction. Okay, in case any of you didn't grow up with like regular clocks that had hands going this way. Okay. Does that answer your question?
Yeah. Thank you.
I guess that's the answer. Sure, you're welcome. Does anybody have any other questions? Do you have any other questions? Anybody over chapter 1?
For number 25, to prove the reverse triangle, do we just follow the same proof as the triangle inequality that's in the book?
Let's see. I think you can, but I think what might be better is to just use the triangle inequality. And let's see here. Has anybody done that successfully? You want to make a comment?
No, I just thought doing the triangle inequalities too. I pretty much just did the same.
You use the triangle inequality because it's a corollary. That means it follows from the triangle inequality. So that means that what? Yeah, so what you can do is you can you can like, let me just give you some hints, some ideas that you can explore around with. So you could like come up with, so like these are small Z1, Z2. So you could come up with like big Z1 and big Z2 and let them be some kind of combination of these. So maybe that's like Z1 plus Z2. And maybe that's Z1 minus Z2. This might not work. You could do some combination like that and then apply the triangle inequality to that and see what happens. Okay, or maybe Z2 could be just Z1 or something, or it could be just like that. Okay, or maybe it could just be Z2, little Z2. Okay, but the thing is that you apply the triangle inequality with these. You start out with the modulus of Z1 plus, this is capital Z1 plus capital Z2 is less than or equal to capital Z1 plus capital Z2, and then like if this was Z1, this is Z1 minus Z2 there, then when you plug it in right here, it would be little Z1 plus little Z2 plus little Z1 minus little Z2 right there. And you're just plugging in those values there. You start out with the triangle inequality there, and then you plug those values in here, and then you kind of see what you get over here. Okay, and then maybe things work out, maybe not. Maybe you modify it. Maybe you go back and say, let's make it be. Maybe we can make this one be negative Z1. Okay, so then when you plug it in, then you get, and maybe that's Z1 plus Z2. Maybe this is negative Z1. And then you plug it in and something different happens. Okay, so those are different. So that's, I would explore doing that kind of a thing. Okay.
Mm-hmm. How about number 26?
26. This one?
Yeah, please.
Okay. Okay. So number 26. One thing to note with number 26 is that this part right here, this means that the modulus of Z equals 2. Being on the circle, this is circle center 0 and radius 2. That means that your modulus is going to be 2. So that's another way of writing this circle right here, that the modulus is 2. And so with that information, if you use, so let's say this left-hand side is going to be equal to this. And if you do this, if you split it up into 2 pieces, wait. So you have a 1. Okay, so you have modulus of Z squared minus modulus of 1. Okay, which of these is bigger? This one? Okay, just looking at the denominators. This denominator or this denominator? According to the reverse triangle inequality.
The first one, to the left.
Yeah, so this denominator is bigger than that one, greater than or equal to that one. But they're in the denominator, so this inequality is going to go like that, right?
Yeah. Because
this is bigger than that. And so that means that, like this is larger. So imagine, let's say this was something like 3. So you have like 1 pi among 3 people. But then let's say this is smaller, so that's only 2. So that's 1 pi among 2 people. So each one gets more pi, right? So this is bigger. And then you plug that in. So this means that if you take the modulus of z, well, the modulus of z squared is the same as modulus of z squared like that. Okay, so modulus can do this kind of stuff. Okay, so that's going to be 4. And that probably showed you too much. Okay, you should be able to finish it from there.
Yeah. Thank you.
Okay. Sure, you're welcome. Any other questions?
With the area in 29, I'm just a little bit confused if it looks like a circle or they are like straight lines with boundaries. I don't know if you know what I mean.
Wait, which one are you talking about?
29.
29. Oh, this one here?
Uh-huh. With just the boundary. I mean, just the graph that it looks like. Is that like a couple of straight lines? Or is it like a circle? I'm a little bit confused with the concept of z.
Okay, so this right here is going to be a line segment. That's going to be a line segment. Because if z is real, then that's just going to be a line segment. And it's going to be on the, so like if we have a graph of this right here, so that part is just going to go from -2 to -1. So it's just going to be this line segment. Well,
okay.
For modulus of z less than 1, this is going to be, that's the line segment. This is going to be an open disk. Okay, so that will be like this. And then these are just going to be points.
Okay.
So 1 and 2, which is like right there and there. Okay.
So how do you tell if it is a point, like a line segment, or a point, or a disk?
I guess you get it from experience, but you kind of have to follow what they're trying to tell you. What they're trying to tell you. So z is real. That means that you got to be on the real axis, right?
Mm-hmm.
And then they put this restriction here, so that means it's a line segment on the real axis. And then this right here, so you don't. So this right here just means this is also we went over circles and disks, and this is how you denote a disk, which is the inside. And then equals would be just a circle. Equals, like this one right here, equals. That would be the circle of radius 2. So if that's 2y and that's 2, then it's going to be just that. That's what this is right here. Okay.
Right.
So as you get further into the course, this is really important to know, especially for like really later on, that this right here, immediately see that, and that's just a circle like that.
Okay.